Literally right before recording this video, I realized I put my pants on inside out, and that was really fun. So anyway, today we're going low effort. I feel like the last few videos we've been doing p-adic numbers, we've been doing quaternions. Those took a long time. So I want something that's just quick, easy, you know, something I could do before I go to bed tonight and hopefully finish within a half hour. So I thought it'd be cool to learn more about the Bernoulli's equation. I don't know if this is too crazy, but I found this video that's like 6 minutes. We're going to watch this as an introduction, and if it's good, we'll keep going with it. So this one's called Bernoulli's Principle by Get A Class Physics. Yeah, let's go into it. Get A Class. Oh, it's Bach. No, that's Albert Einstein.
What will happen if we create a strong airflow between two balls suspended on threads? It seems that...
Oh, I like you can just see the guy filming. He's just it's kind of sinister. I feel like that's like what you see in a horror movie or something, like dun, 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 dun.
Create a strong airflow between two balls suspended on threads. It seems that the flow should push the balls apart. We switch on the blower and, surprisingly, the balls get attracted by one another. They are rotating, which means the airflow is getting through between them. Why isn't it pushing them apart? Let's carry out another experiment. We attach a funnel to a hose and switch on the blower.
Who is this guy? I love this guy. Like, he's just so happy. He looked down that hose and he saw something we didn't see. That's so funny. I need to know his name. I guess I don't see him. I'm gonna call you what's his name? Oh my gosh, I'm blinking so hard. Oh my gosh, it's Danny DeVito. Holy guys, I just went through this whole rabbit hole. Like, I know this was off camera, but I swear I spent 2 minutes blanking on this guy's name. And I was like, who said... I looked at the... So anyway, I started blasting meme, because I know that's where he's from. And I literally could not remember his name for the life of me. It's Danny DeVito. Who... I'm so stupid. Anyway, I'm going to call you Danny, because you remind me of Danny DeVito.
Then we put a rubber ball into the funnel. Instead of bouncing out of the funnel, it gets sucked into
It's this party trick.
We
So I get all the
funnel
women.
upside down, but the ball isn't falling out of it. So why does the airflow hold the ball in the funnel instead of pushing it out?
Look, Mom. Look what I did.
Experiment can be conducted with running water. If we put a tennis ball next to it, the ball sticks to the water and hangs there on an inclined thread. It looks like a fast flow of gas or liquid possesses counterintuitive properties which need to be explained. To do so, let's consider water flowing through a pipe of variable cross-section.
This is a bottle of swig.
When the cross-sectional area of the pipe decreases, the speed of water flow increases. According to Newton's second law, in order to increase the speed, some force must be applied to water. Thus, the pressure in the wider part of the pipe must be higher than that in the narrower one. Therefore, when the pipe gets narrower, the pressure in it will not rise, as it may seem at first sight, but fall. This puzzling paradox is called Bernoulli's principle in honor of its discoverer, a Swiss physicist, Daniel Bernoulli.
Okay, now I'm getting this. I'm picking it up.
We made this narrow neck pipe from two plastic glasses. When we blow it, the
And watch as our assistant deep throats it.
air pressure at the exit will be equal to the atmospheric one. This means that inside the narrow neck, it will be lower than the atmospheric one. To check this, let us insert a tube into the wall of the neck, connecting it to a pressure sensor.
Ah, there's that
When we
smile.
blow the pipe, the sensor shows the decrease in pressure by 5 kilopascal, which is 50 centimeters of water column. Let us put the lower end of the tube into the vessel with colored water and blow the pipe again. We can see that the water makes a 30 centimeter rise. To increase the pressure even greater, we'll connect the pipe to the blower, which provides a far higher speed of the airflow. We switch on the blower, and what we get is a perfect water sprayer.
A perfect water sprayer.
Now let us attach a plastic bottle to the pipe and switch on the blower again.
Oh, that's my rib cage right there. Holy mercy. That was, hopefully they don't hook me up to a Bernoulli's vacuum thing.
That's incredible. A decrease in the internal pressure causes the bottle to be crumpled by the outer atmospheric pressure.
Ooh, mamacita!
Let us consider water flowing inside a cross-section pipe. The volume of water V enters the pipe from the left end and leaves the pipe on its right end. The difference of pressures at the ends of the pipe does mechanical work, which equals P1 minus P2 multiplied by V. When there are no losses, all this work goes to increase the kinetic energy of water. Mass is the product into the pipe.
Huh? Yeah, I'm just doing the Bernoulli's principle video. I'm just getting to understand it more. The equations are kind of right now. Like, this equation saying that the work done on the water is P1 pressure minus pressure 2 times the volume.
I don't know if I've seen that, but pressure is force divided by area, and work is force times distance.
Then you would have a dimension of V, because area is 2 dimensions, volume is 3. So you'd have a force times a distance, which would be work. So this is a thought thing, right? Me and my roommate were just talking that in this equation right here, this is the P1 minus P2 times V is the work done on the water, right? And pressure is force over an area, right? And then we're multiplying volume. So if you do F over A times this V, then the area would be measured in meters squared and the V would be measured in meters cubed. So when you multiply it, the 2 meters cancel out and you're left with a force times a distance, which is the work. But I'm not too sure if that's exactly it because I don't think there's work on liquids apparently. But anyway, that's just like kind of where my thought process is right now. I have no idea what this is going on, going to be honest, but we'll keep going. Well, like MB squared, right? MB squared is kinetic energy. So this is, I don't know. That's just what I think of, but.
The value of rho V squared divided by 2 is called the velocity head of a fluid. According to Bernoulli's principle,
it's called the what?
It's called the velocity head of a fluid.
Velocity head of a fluid. Let's search that up. But you notice when I type, like look down at my keyboard, my typing skills go up like 1,000%. Yeah, I'm just built different. Velocity head is the pressure which is needed to increase the speed at which a liquid flows. Okay, I can get behind that. So this equation represents the pressure needed to increase the speed of the water. We'll figure it out.
According to Bernoulli's principle, the sum of pressure and velocity head in an ideal fluid remains constant throughout the whole pipe. This equation allows to measure the speed and volume consumption of a gas or fluid flowing through the pipe. To do this, a special device is inserted into the pipe. It is called Bernoulli tube by the name of its inventor. A differential pressure sensor is attached to the tube. It measures the difference of pressure between the narrow and the wide sections of the pipe. The speed of flow calculation is based on this difference. Let us switch on the blower. The device shows that 12 liters of air get through the pipe every second. This means that if the section of the pipe is 3 square centimeters, the speed of air within it is 40 meters per second. Ventouris look much more substantial. They can measure the consumption of gas flowing through the pipeline with minor pressure losses.
Interesting. Is this just the end of the video? Is Danny just gonna do this to us for like 30 more seconds? He was so fascinated by that. He's like, guys, at the end of the video, can I spin the ball really fast in the cone, please? And they're like, fine, Danny. And he did it, and he's a legend for it. So anyway, yeah, that was it. That was a cool introduction. I kind of get, okay, let's talk about what I get. I understand this part. I understand how like the velocity as it goes through a smaller pipe is going to increase, thus causing a decrease in pressure. So the pressure on this side is going to be bigger to compensate because of conservation of, I guess, energy. I can just say that. This experiment was kind of cool to show that, how like the lack of pressure causes the bottom part of the tube, right, the water, because there's more pressure down here, to shoot up through the tube. That was pretty sick. Getting to watch my rib cage get just absolutely compressed here was pretty sick too. Okay, here I got this part. So this is the amount of volume of water going through the tube at once. This is the same volume. So eventually we can imagine like it starts here and it flows over here. The work done, we talked about this, the work done to move this water across is going to be P1 minus P2, which we talked about as a force times an area, the force of the area of this circle, for instance, times the volume of the water. So it's distributed from here to here, this volume. So we're left with work. And then I think it was right here where I kind of got mixed up. Mass is the product of volume times density. That does make sense, right? So I guess this is an equality here.
The volume
Let's kind of break this down, right? So we know that what she just said, right? The density is mass times volume, right? So this is density. Why is it squared? Can you write it out? MV, so density times V over 2. There's something going on here I don't understand. Or maybe it's just I lack the math for it. So anyway, don't understand that completely.
The value.
And then we talked about this. This is the head volume. Velocity, sorry, head velocity is the pressure needed to increase the speed at which a liquid flows. So that's what this thing is. I don't know what rho means here. I don't remember her labeling it.
Square divided by 2 is called the velocity head of a fluid.
So is this just like a pressure? I'm not too sure. The problem with 3D Pokemon. I love that video. That's so sick. I've never seen it. Yeah. And then this last part kind of got me a little lost. I'm not going to lie, I zoned out a bit. But cool introduction nonetheless. I think this is a good place to stop, honestly. Keep this video kind of short, and I'll see you on the next one.